Long ago, hidden in the nucleus of the cell, there was a strand of DNA that created a chromosome. The DNA knew everything, how to create their day-to-day proteins that run the cell. The genes passed on to the cells inspired by their culture, and had enzymes to help replicate it in an ancient ritual they called the replication.
Hadouken!
To start out the replication, the great helicase enzyme warriors broke the strong hydrogen bonds between the DNA strands. They broke the bonds between the 4 great nucleotides. The bonds were broken between each of the awesome adenine and tough thymine, and the bonds between the superb cytosine and great guanine. This part of the ritual was called unzipping. While the helicase continued to break the bonds, the wise polymerase went to the leading strand of the unzipped DNA, read it in the order of 5' to 3', and added one of the 4 great nucleotides to the nucleotide it is paired with. Awesome adenine with whatever, I already told you which one goes with which. Meanwhile, the enzyme apprentice of the polymerase, the primase, went to the lagging strand of the DNA and did a job very similar to that of the polymerase, and attached RNA nucleotides to the DNA strand. The RNA was slightly different than the DNA strands. The RNA nucleotides replaced tough thymine with unusual uracil. This nucleotide isn't fitting into the adenine. Why are you attaching RNA nucleotides to this? You are supposed to be duplicating the DNA, and that requires you to place thymine, not uracil. Master Polymerase, if you just read the sequence, I'm sure you'll be pleased. No! I worked hard on that. And so polymerase replaced the RNA sequence created by the primase with the DNA nucleotides wished by the cell. And so they had created 2 duplicate chromosomes. The end. Why you not tell better story? Why you not be happy with what I give you? DNA strand knows all, but it cannot leave the nucleus for its own safety. We need a messenger. I've got it! I'll use the primase's idea of RNA. The unusual uracil replaces the tough thymine, if I'm correct, and the messenger RNA should be able to go through the endoplasmic reticulum to the ribosomes. And so the polymerase read the DNA sequence and created a matching messenger RNA. To keep the mRNA together, he created a phosphate sugar backbone to keep the messenger RNA together. Now remember, your job is simple. Get to the ribosomes. The 3-letter codons can only be translated into amino acid sequences there. Our cell is in a time of need. We need an amino acid sequence to become a protein. I understand. And so I said, Conrad, she's not the right molecule for you. Maybe if you stop taking in her electrons, you'll feel more positive. Oh, I'm funny. Foreigners. Oh, hey, I'll talk to you later. I have business to take care of. So, you must be the messenger sent by the DNA. I believe you have something for me. Yes. I haven't seen this sequence in quite some time, but I think this old organelle can do the job. How do these things code for proteins? What, this? It's pretty simple, really. Here, come, I'll show you. We take the first codon and put it here in the P site. My tRNA workers have anticodons, which kind of just bond with the codons, and they have one of 20 amino acids that go with the anticodon. All the other codons after the first one get coded in the exact same way at the A site, just behind it over there. Once a codon is done at the P site, they send it over to the S site, but the amino acid stays at the P site and builds up right there. And then the tRNA leaves with anti-codon and goes makes use of itself. And then the codons keep getting coded at the S site, the amino acids pile up at the P, and the tRNA leaves at the S. And this keeps going until we reach the stop codon. The amino acid breaks off, we have a chain, and we wait for it to fold itself into the protein needed. And the stop codes are... We think the codons UUA, UAG, and UGA tend to stop the translation, and that's when they tend to break free. Oh, looks like the RNA has been translated. Heh, now we just sit back and watch.